Okay. So thank you, everybody. I'm Didier Schwab. I'm a professor here in Grenoble, and I'm here to introduce one of the members of my team at League, Maxime Peyrard. So, Maxime, you have something like 35 minutes or something like that.
Okay, thank you very much, everyone. So thank you for the invitation. So for this presentation, we'll speak a bit about interpretability. So in the recent progress of LLMs and the fact that they have been deployed a lot in many usage, it became a bit more important, or people became a bit more interested in interpretability questions. And I think it begs now the question of how to actually do this kind of research in a principled way. So in this presentation, we'll just try to stay fairly high level and give some overview about some types of methods and some of their limitations, and trying to think about what would be maybe a way forward to get some principled research in this direction. So we might want to start with the question of why would we care about explaining or interpreting. So there are some obvious practical reasons that have been of interest for some people. So like, for example, transparency and trust. Whenever we engage in exchange with generative AI systems, we want to understand how they work for these transparency reasons, but also for some legal requirements. For example, if you deploy your AI system in the world, in your company or government or whatever. There's also these aspects of understanding the types of errors that are made. So this idea of continuous improvements or robustness to be able to predict what types of error would be made. And there's also some reasons for communication, like communications about the abilities of LLMs or generative AI in general, or their limitations, especially in the case when humans and will collaborate with AI or interact with AI systems. And there could be many others. All of these are very practical reasons, but I think as scientists and researchers, there's also some deep scientific questions that is interesting in this topic. And this is the idea of, it's one instance of a more general problem, that is the problem of explaining complex systems. So there are many complex systems that are of interest to science. So for example, the brain, and there is this whole field of neuroscience whose goal is to actually explain the brain, like explain some behaviors by looking at the brain. So for them, it's interpretability of one complex system, which is the brain. There are some other complex systems of interest, like the climate or climate models. So the idea is now to understand, predict what will happen in this specific type of complex system, that is the weather and the climate. And for another example would be the immune system. It's also a very complex system that is a higher interest, because understanding how it works might have far-reaching consequences when we want to, for example, develop drugs or fight disease or understand some kinds of diseases. So many of the scientists in these other fields of science have themselves realized the interesting aspects of AI. It's because AI is the simplest complex systems, in the sense that compared to all of these other complex systems that we talked about, AI is fully observable and fully manipulable. So like we can do whatever we want with an AI system that we cannot do with a brain. Like we can observe every single detail of it because we craft them, and we can manipulate every single system or every single subset of it because we simply just have access to it. So this has been recognized by other scientists as a very great test bed to test the methods and the formalisms, the framework, the ideas that they have in their own field, testing them in this type of complex system, because if they are not even able to explain AI, then it would be even harder to explain other type of complex system when you have less access to it. So it's an interesting point of where different fields of science can exchange ideas on these deep scientific questions. And so this is kind of a bit of a motivation, but now we can start to look a bit then in the realm of generative AI, like LLM especially, what has been done a little bit. So we'll take some high-level overview of these different ways of providing some explanations. The first one is kind of the simplest one, is kind of behavior. So we just observe the behavior, and what do we mean by the behavior? It means that the AI is just whatever it is, it's a black box, it just has some input and output, and we observe how the outputs are related to the input. And in this case, if we carefully craft some input, we can measure the effect on the output, and we can slowly build some understanding of what type of behavior are present in the AI system, or any system in general, actually. So one of the most obvious and simplest use case of behavioral testing is benchmarking. There are some type of inputs that we care about, and AI is producing some output for this system, and then we just compare them to something else that we care about, and usually we put some score on it, and it's able to just rank or compare different AI systems. It's a very, very simple type of behavioral testing. It's just, is this capability present to what extent in the system? But more, a bit more interesting could be the fact of trying to understand some aspect of the behavior a bit more precisely that we might care about. So imagine we have different types of input, we might have then different types of input, and we might be interested in trying to understand, if I modify the input in such and such ways, how will it modify the output? So what will be the effect on the output? So this has been subject of a lot of research in the past. There's some mathematical formalisms to understand this. But just to give two more recent examples in the world of LLM, there is this first one that simply takes a question that is sent to an LLM. The LLM is then capable of producing the correct answer, but correct reasoning, something that looks like correct reasoning and produce the correct answer. If you simply add a little modification to the input by repeating one sentence twice, then the reasoning becomes different and wrong, and the answer becomes wrong. So this is this kind of thing that is a bit worrying when we start to do anthropomorphization, and we would expect that the LLM would not have been susceptible to this kind of perturbation, but it is. And the second one is even simpler, it's just paraphrasing, changing some words for their synonyms, and the answer changes. So these are some examples that, like, the behavior of LLM is kind of suspicious, but then we can take this idea and imagine any kind of modification of the input and measuring any kind of things that we care about in the output to slowly build an understanding of what type of behavior we are expecting to observe. There is another way to systematize this a little bit more, it's a bit more mathematical, is to look at the features, so it means the mathematical representation that the generative AI is using to represent the world, and to do some types of importance measurement, trying to say what was the impact of this feature mathematically on the output. So there has been a lot of work in this direction. Is actually one of the type of work that were very older, like more foundational for the field of interpretability. So we don't go too much in details in these ones because they're a bit more mathematical. And then there is also, with the advent of LLM, this whole idea of LLM psychology. Just because they produce content and they can consume content that look like human, there was this idea to actually give the LLM some psychological tests to see what type of psychology they might have. And so it's this quote that says, like, machine psychology aims to elicit mechanisms of decision-making and reasoning in LLMs by treating them as participants in psychology experiments. So this is very simple to do because the psychological tests have been made for humans, so you can just give them to LLM directly in natural language. There are many problems with this idea of LLM psychology, and the first is like anthropomorphization, where you think that giving the test of LLM that you give to human will have the same predictive power as it has for humans, which is clearly not the case, and it has been shown in many ways. Like, you just change the prompt, you have different results, so there is no real valid definition of a psychology for an LLM. But there is this field that emerged, and there's some interest in it, so maybe it will, over time, people will find better formalisms and better ways to define what they mean by psychology and LLM psychology, and find some formalizations that actually are useful. So the big problem with all these ideas that we've seen just now is that they are very behavioral, only behavioral. They only look at the input and the output. So there is still some human researcher or maybe some automated methods that look at the input and the output and the patterns that they observed in the behavior, and will make some hypothesis about what is the explanation. This will be this high-level explanation, saying because when I give this kind of input, there is this kind of output. When I give this other kind of input, there is other kind of output. So there is some high-level explanations. But the problem is that we are never sure that it's consistent with the actual low-level computation that happens inside the LLM or inside the generative AI. So this could be that the explanation is just an after-the-fact, story that is not supported or sustained by the actual computation that happens. And for the field of LLM psychology, is what we said, it relies on unrealistic assumptions. So for now, it's not really useful or not really giving results that can be generalized to other types of behavior in the LLM world. So we say, okay, we didn't look at computation, so the next step is actually let's open the black box and look into the computation. And this is the field of neural correlate. So the whole point is now we look at the actual computation that is happening while some behavior of interest is happening. So one way to think about it in simple terms is that we have usually the generative AIs are some neural network in some ways, so they have some activations, and we start with the activations that they have, so the value that they have at different subsets of the neural network when they are processing some input, and we convert them, all of these activations, into some vector that collects all these activations for each individual input. And then we do some study of these patterns of activations for whatever behavior of interest we want to study. So typically, we would have, for example, two behavior. So when the LLM, for example, is engaged in behavior A, we collect different examples of its activation. So for some input, it produces behavior A. So we classify its pattern or its activations for this input into behavior A. And for another different input, it will exhibit behavior B. So we collect its activations into the groups of behavior B. So behavior could be anything that we care about, anything that we want to measure. For example, whether the LLM is producing a factually correct answer to a question or a wrong answer to a question, like an hallucination, or whether the LLM is talking in the present or speaking in the past. It could be anything that we could be interested in. And then once we have these two groups, we just compare the patterns, this statistical analysis on the patterns of activations, and we say, can we find some features that distinguish behavior A from behavior B from the activations, for finding some patterns of activation that distinguish between the two behaviors. So here's one example that we had at some point in the past that was we had this for humor data set that was generated by humans. So there were some satirical headlines that come from the Onion, like the satirical website. And then humans have been asked to modify these sentences in the minimal amount of edits that they could to turn satirical sentence into serious sentence. So this gives like paired sentences with minimal differences where one is satirical and one is not satirical. And then what we did is simple, the same idea. We feed these kind of sentences to some LLM. We collect their activations. And wherever there is a satirical sentence, we put them in some group. And whenever they are in non-satirical sentence, like serious sentence, they are in the second group. And we can compare the activation of the serious and the satirical sentences in a pair and repeat the comparison over the full data set. And something interesting that could be found is that, surprisingly, there is just one attention heads that activates a lot on the modified part of the funny sentence, and only in this case. And so this finding is quite robust, because if you go and you knock this head off, your LLM will predict that the sentence is serious and not satirical. So this one is actually predictive of how you will classify your sentence, whether it will be funny or whether it will be serious. So this is one interesting aspect, to find that the computation is actually giving us some information about the behavior of the LLM, and that we can track it. This I will skip, it's too technical. Then there is the idea of probing, and so it was talked about before in the previous presentation. Probing is a very general and very much used idea to generalize a little bit what we said before. Now we don't necessarily have one or two behavior. We might have any types of label. So we have some activations, and for one input we have one activation, and then we have a label. It could be a behavior, or it could be a number, it could be anything, but some label that we are interested in. And then we simply perform some machine learning task, like could be a linear regression, could be also sometimes a bit more sophisticated algorithm, but we try to predict the label just from the vectors of activation. And so this is quite simple, like the label could be the same as before, some behavior like hallucination or not, and this is actually the example in this paper, where what the author did is that they collected some sentences for which there were some factually correct tokens that were generated by the LLMs, and some tokens that were actually hallucinations, so factually incorrect tokens. And they asked humans to label them. And then they trained some probe. So the probe was looking at the activation in some layer of the LLM. Can I predict whether this token is correct or wrong? And so they used some data, training data, to train the probe, and then on some validation data, they were using the probe to see whether the probe was capable of making these predictions. And here in this plot, you can see, like on the right, they collected all the hallucinated tokens, so like the factually wrong, incorrect token. And the more yellow it is, the more the probe is saying that it's hallucinating. So in this case, they were making the hypothesis that the probe was capable of distinguishing between hallucination and non-hallucination. So actually already as part of the computation, the LLM was computing differently whenever it was producing a factually correct token from a factually incorrect token. And there were some subsequent work that showed that you can go in this activation, modify them. So if you modify them and then you let the computation run, you can actually produce more factually correct or more factually incorrect, depending how you manipulate. So this is another example that the computation gives you information about the behavior. Maybe the most foundational, like the original idea comes from this work. This work, like one of these work, was trying to predict some linguistic features. So you train some model, some language model, for example, to do something, some task, like you fine-tune it to do some task. So in this case, you train the LLM to do some relation classification. So you fine-tune it to do some relation classification. And then what you do is you train a probing classifier. So you take some subset of the activations, some activations, and from these activations, you try to predict something else. So in this case was some linguistic features about the pause tags and so on. And if your probing classifier is capable of predicting these linguistic features from the activations, then the hypothesis is that these features contain, this activation contains information that is relevant for it. So it's a bit as if the language model has learned these features as part of its training for another task. So this was original idea of probing that wanted to show like we can find something that looks like linguistic features in the computation of the LLM that was not trained for linguistic feature. So it was surprising, and it was also like motivating for the field of probing. There are some problems with probing and some limitations with also the methods that we talked about before that were special cases of probing. Is that probing is actually a statistical analysis, so it's a machine learning problem, and it has all the problems of machine learning, especially the problem that activations, especially for LLMs, are very highly dimensional, and it's very easy to overfit. It's very easy to overfit. It's very easy to think we have found something by probing, and actually it was just a statistical fluctuation. So there were some difficulties to reproduce some of the results when you change the domain, or for LLMs when you switch the prompt. So there is some worries to have that the method is a bit tricky and has to be done with care. But even more generally, there is a problem with the whole idea of looking simply at statistical patterns of computation to make an explanation. Is that being able to predict something from the activation doesn't mean that this pattern of activation was what caused the behavior, was the actual explanation of the behavior. So this idea of predicting is not understanding, because correlations, which are what we talked about, do not generalize. It could be that this pattern was just there for some other reasons that were more early on in the computation, or like not easy to catch statistically in the statistical analysis. So there are some of these papers that make these claims a bit more formally. So we said that correlations are not enough for explanation. So of course the next step is to look for causal analysis. And looking for causal analysis, the main idea is to perform some intervention, like saying if I modify this aspect of the network, will it have the modification that I think it should have? And this is where LLMs are very convenient, because we can do this as much as we want, provided some computational limitation. But it's something that we cannot do in the brain, for example. We cannot go and modify each and every neuron up until we found something of interest. But we can do for LLMs. So people have done it. But the first idea is to just take the idea of probing and say, once we have the probe, let's validate further the probe by saying, if I do the modification that my probe is telling me to do, then I should observe a different behavior. So this idea of amnestic probing is a bit like if we were to do knockoff in the brain, like if you remove some neuron that you think is associated to some behavior, if you go and you remove this neuron, then you should see the behavior disappearing. So this was the idea of amnestic probing. You have a probe that tells you there are some linguistic features, and then you say, okay, let's modify my activation such that the probe is fooled and doesn't believe that there is the behavior anymore, that doesn't believe that there are the linguistic features anymore. And then with this modified activation, I let the computation run. Does it remove the behavior or not? And so it's something that actually Martin in the previous presentation was actually doing. They were doing probing, and then later on they were making the modification to see different behavior. So it means that we should validate the probe by further manipulation of the computation. But then the idea was taken to be formalized more generally with the framework of causal mediation analysis. So this is just a framework to understand what's the impact of some model components on the behavior of the overall model. So imagine we are in the standard LLM setting. It's going to predict the next token by doing some of its computation with this complex neural network architecture that it's doing. And we just ask the question, what is the effect of this component on the prediction and this specific prediction that is doing now? Why is it the token Paris that has that much probability and not another one? And you can ask, what is the contribution of this component? What's the contribution of this other component? And so on. And this is a very general framework that is used all over in sciences, the framework of causal mediation analysis, where you have some variable x, which in our case is the input, and some variable y, which in our case is the output. And we know that x influences y. So if I modify x, it will modify y in some ways. So in our case, it's clear that if we change the input, it will change the output. But the question we might be interested in is by which ways, by which mechanisms does the effect of x is transported into y? So how much of the effect of x is explained by some path or some other variable that we call m, by which the causal effect is passing through. So an example typical example would be, for example, we know that exercising increases lifespan, but we might be wondering then, okay, fine, but by which mechanism does exercising increases lifespan? Maybe it's because the mediator, like the variable in the middle, M, is it because when we exercise more, we have some changes in the body composition, and these changes in the body composition increases lifespan? Is it because when we exercise more, we have more dopamine or whatever in the brain, and this increases lifespan? We can be interested in disentangling the different mechanisms and saying by which amount, which path explains the effect. So this is a very general framework, has some ways to perform the computation, some ways to think about the problem, and we can apply them directly for LLMs, and it's very convenient in LLM because we can run whatever experiments we want. So we can do this analysis very easily. So it was recognized several years ago, and people have used it for studying the problem of gender bias in LLM. So imagine you give the prompt to some LLM like the nurse said that. So this is the input X, and you look at the output token, which is like a pronoun, and you look for the she or he tokens, and you look for the relative probability distribution. Now imagine if you were to do a modification, like an intervention on the input on the prompt, and you modify the nurse by the doctor. You might see, and for several other LLMs, you do see changes in the probability distribution of the pronouns, and you observe some gender bias. Therefore, in this case, you say that there is gender bias. And now the question is, where is the gender bias happening inside the computation? What are the places where the computation is actually deciding to change the probability distribution? And you can do that by applying these tools of causal mediation analysis. So we don't go in the details of how it works, but basically you can ask for every subset of the network, how are you responsible for the change in probability distribution when I modify the input? And what they found in this paper is that there are very few heads that are actually very responsible for this change, so for this gender bias. And then what they did is the same as when we do probing. You can come and you can modify these heads and see if it removes the gender bias or not. So in this very simple example of gender bias, how they define them, they were able to remove most of the gender bias just by modifying these heads according to the output of the analysis. So this is an example. Another example is the one about factual recall. So the ability of LLM to know some factual knowledge about the world and to recall it when they are prompted to do so. So for example, you ask an LLM, the Eiffel Tower is located in, and you look what's the next token that they produce. If they produce the correct token, you kind of say that the behavior is a factual recall, so they have been recalling a correct factual information about the world. So in this work, they looked at this type of behavior, and they applied the same tool of causal mediation analysis. And by applying this tool, they were able to find out that there are very few places in the network, so it's these MLPs, very few components in the transformer, in the architecture of the LLM, that are very responsible for the ability to reproduce the correct token of a factual question. And so the hypothesis was that these very few places are acting as memories of factual knowledge. And this has been further validated by manipulation of these places to change the factual knowledge. Like if you do targeted modification, you can change the factual knowledge. So the LLM can actually have this very localized behavior. So let's keep this. But we still have some difficulty, is that all these neural level explanations, they have the problem that they are not even at the correct level of abstraction for many people that would be interested in some explanations. It's like, what would it mean to tell to someone, yeah, your LLM is having gender bias because this component is having this value? It's not really insightful. It fails to instill a sense of understanding. And also there is some criticism, and we have actually some experiments with in our group to show that it's a bit too easy to find explanations in this way. We can find basically many explanations that are very contradictory, even in random neural network. So it's a sign that the methods that we use are actually not good enough for finding valid explanations. So just to finish in the last few minutes, we want to think a bit about how to do rigorously, like how can we imagine a path towards doing something more rigorous. So one thing that we can take inspiration of is to come back to this other field of science, is the problem that they have. So they have been thinking about it for quite a while. And let's look at neuroscience. So they have the same problem, input, output, it's the behavior, and they have the brain that they can measure to some extent, and for which they can do intervention to some extent. But the problem is that they have been doing that for a while, and they have statistical analysis, causal method analysis. But the question is, how do they know that their methods are correct? Because they never see a brain, a behavior, and the actually correct explanation. So maybe their methods are not wrong, are not working, and they cannot know. So they have this big problem. But there was this very clever paper, this very inspiring paper. They could a neuroscientist understand a microprocessor? And the idea was like, we know everything about the microprocessor. It has been engineered by humans. So let's treat it as if it was a brain. And the transistor inside, we say they are like neurons, and we can measure them, whether they are on, off, or the level of activations. And we can intervene. We can knock off every transistor that we want, or we can change their value whenever we want, however we want. And let's see if our method of analysis can recover anything that is meaningful about how the microprocessor works. So can the method that they use work in this setting, where the microprocessor is arguably much simpler than a brain, and we have full observability, contrary to the brain, and where we have full manipulability, contrary to the brain? And the answer was like big no. Nothing can be recovered. Nothing meaningful can be recovered. Here is an example, like if you do the causal mediation analysis, which for me was a bit sad because I thought causal mediation analysis was super nice theory to think about explainability. But here they did something like causal mediation analysis, and this is the outcome, and it's completely uninformative. It doesn't tell you anything about the fact that there is a CPU, the fact that there are some registry, that there are some memories, local memory, and that they exchange information through some channels and so on. It tells you nothing. So the problem is that for neuroscientists now is like maybe they have this difficulty that nothing that they do might make sense. I mean, it's not that bad because they have many ways to further validate what they are doing. But probably for them it would be a bit worrying to say that we cannot explain the microprocessor. Should we do something else until we are at least capable of explaining the microprocessor? But for us, we have the same problem. So before making fun of neuroscience, maybe we're in the exact same spot. We just have the exact same setting. And how do we know that the explanations that we produce are actually correct? Because we have also almost never seen example of LLM setting, a behavior, and the correct explanation for the LLM. So the point is that we would like to find what's the equivalent of a microprocessor for us to have a problem where we know the exact answer and to be able to solve it. So this is the work that my PhD is doing for his PhD, and he will talk about it now in the next few minutes, so I will let the floor to him. That's it for my presentation. Thank you.
Thank you, Maxime. Maybe there are some questions in the room. You wish that Maxime present and then you will answer both to the questions? Oh.
So nice. I think there are some limits between the parallel you are making between brain studies and chips or artificial intelligence. Is the fact that a lot of things that have been learned on neuroscience are due to pathologies of brains. In fact, to discover that you have specialized parts of the brain dedicated to decision making or whatever cognitive functions is due to the fact that you have pathological humans which have deficits of whatever and so on. So to learn somehow the normal behaviors of humans, you have the exemplars of pathologies. So what would be the equivalent for I.
Thank you very much. It's a great question. So for the pathologies, actually we could replicate pathologies if we wanted, because it's kind of an intervention. Like we said, actually these people function differently, so they have different behavior, and it turns out that there are something different in the brain. So then we make the hypothesis that there is this thing is responsible for the different behavior. So in theory, it should be covered by causal mediation analysis, saying like if I were to modify this, if I do enough intervention, if I were to modify this part of the brain, I would see this different pathology kind of. But the problem is that that's what they saw in the could a neuroscientist understand a microprocessor, is that what intervention is meaningful is the space of possible intervention is just so big that we need to have these naturally occurring kind of events so that we even form good hypotheses, which is one of the problems that we have now, is that we don't have naturally occurring event. Like we could imagine, but it would be too costly for OpenAI to train pathological GPT-4s just for us to do by changing some aspects of the training data just for us to do. But it's a strategy that some people have, like to take training runs that failed to look also in the computation, but it's very difficult. Like I don't think there are good ideas for now to how to do it systematically.
Yeah. Just a feedback. You know, this large language model are trained on non-pathological language production. I think that it will be very helpful, in fact, to study impoverished production of language, for example, like children or whatever, or elderly person with strokes and so on. So there is, at my opinion, for academic people, in fact, there is a place to be taken for studying pathological language production.
Yeah, it's a good point. Yeah, it's a good point.
Thank you for your talk. I got the feeling that our brain has properties of fiability and perhaps with redundancy. And if you affect only a small part of your brain, you may still, at the end, a good decision. And perhaps with the synthetic digital neural networks, it may be the same thing. So redundancy and fiability is perhaps a good feature.
Yeah, it's a good point. It's one of the, sometimes when we talk about these topics, we have the worries that is there even one explanation? Because if you remove one path to which the behavior is supported, maybe the same behavior is supported by another path, and so it recovers very quickly. This is what they have shown with fine-tuning. Like you can make some modifications to the computation. If you do a little bit of fine-tuning, suddenly most of the behavior comes back, because there are so many ways in which it was very close to be there. So it's something similar is probably there. It just makes it even more difficult to define what's an explanation. If the explanation can be in different places to different extent, it creates problems of definition, but it's not a problem to not look at. It's just a similar problem that there is there. Yeah.
Thank you, Maxime.
Yeah.
So next speaker is another Maxime Méloux, which is supervised, the PhD supervised by Maxime, the first one, and François Porté. So Maxime, the floor is yours.
Hello. Thank you very much for inviting me. So I'm going to present my work, which is so far called a causal abstraction benchmark for model explainability. And I'm a first-year PhD student under the supervision of Maxime. So basically, one of the goals that we have in interpretability or explainability, as Maxime explained, is that we have some kind of complex system, and we want to be able to understand when it produces some kind of output in a specific situation, what causes it to produce that behavior, what is the process that it undergoes. So here you have a very simple example in which alpaca was prompted, and it was asked to check whether a number y is between two numbers x and z. And this is a task that we know alpaca is able to do very well. And ideally, we want to know how it manages to do that, what is the process underlying this reasoning. And well, Maxime didn't produce that, present that part, but we will assume for this part that to have a correct and a good explanation of a behavior, we want an explanation that is simple, faithful, causal, and global. So if we look at some of the current explainability methods, here I listed some of the main categories of explainability methods. Of course, there are plenty of other ones, but those fall short because, as Maxime explained earlier, they do not completely fit the proposed definition. And here I said that those explanations want them to be causal. So first of all, 90% of explainability methods fail to do that. And even in the one that are causal, they suffer from a locality problem, which means that they will tell you that this component of a neural network is important in its computation, but we don't know in what way it happens, or we never really consider the entire function that is computed by the neural network. In addition, there's a big problem in the evaluation. If we have those methods that produce some kind of output, some kind of explanation for a generative model, how do we check how correct, how faithful that explanation is? We don't have any reference data to check whether an explanation is correct. So this is problematic. So there's this idea that was introduced in the late 90s by Judy Pearl, which is the idea of causal abstraction. And this is a very generic idea, which is that when you have any kind of complex system, not necessarily a generative model, but really any kind of complex system, any kind of process, you can represent it as what's called a structural causal model. And a structural causal model is simply a graph in which you have variables, which are nodes, and mechanisms between those variables, which are edges. So here you have some kind of process where we have 3 input variables, 1 output variable, and some kind of mechanisms and intermediate variables between them. So this can represent, it's very generic, it can represent any algorithm, any kind of process. And what's nice with this very simple model is that you can have different levels of abstraction. You can zoom in, zoom out as much as you want. And you can model parts of your system or your entire system if you want. So let's go back to alpaca, where it was told to say yes if the number y is between x and z and otherwise no. Here are some possible candidates, some ways we may imagine that alpaca performs this computation. So on the left, it might first check whether the number y is bigger than x, and afterwards also check that y is bigger than z. That's one possible way it might be doing it. Another way is that it might be performing both computation at the same time and then checking that both are correct. Or it may be doing something completely different, such as here computing the midpoint distance and comparing it with the other variable. And of course, there's plenty of other ways it might be doing it. These are just some random ideas. And here we can see again the flexibility of SCMs, because we could zoom in any part of this graph. For example, here, where this variable is the sum of x and y divided by 2, we could zoom in and see how the addition is performed, for example. Or here, how is the comparison performed. So we have something that is very modular. So if we think about it, the end goal of explainability would be that given any neural network, we're able to produce an SCM that represents its behavior. So that would be, once we have that, we have everything. We have solved explainability. However, of course, this is extremely complex. First of all, the search space is enormous. You would need to have a list of all possible ways of behavior by me model. Then you would need to check which ones are correct or not. You could have to check all the mappings between the neural network and your causal model. So this is not feasible. And in fact, there's only a few attempts at doing similar things in the literature, but those attempts are very restrained. They make very strong assumptions about the kind of model you're looking for, and so on. So it doesn't really work. And again, we have the same evaluation problem. Let's say we have a method that, given the neural networks, produces a causal model of a behavior of that neural network. How do we check whether it's correct or not? How do we check if it's faithful? So again, we're back to this evaluation problem. So how could we solve that evaluation problem? Well, the reason why we cannot evaluate explainability methods is that we don't have ground truth explanations. So this is the first goal of my thesis, would be to create some kind of test bench where we have neural networks and we have their actual explanations. So this would be, again, pairs where we have a neural network, and for each neural network you have its associated correct explanation. But how do we create those pairs? We do not know how to extract causal models from neural networks. However, something that we can do is to reverse the problem. What I mean by that is that there is a method published in 2022, which is called intervention internship training. And the idea behind that method is that given a causal model that you create yourself, and given a non-trained neural network, you can train that neural network to force it to implement the causal model that you have defined. So for example, here we want a causal neural network to implement this model here. So all you have to do is that define, you tell, okay, I want the neural network to store my variable x in this activation of the network, my variable y here, my variable z here and here, then this intermediate variable should be here, and so on. And then there's an actual training procedure with a specific loss function that is described here. And we can prove mathematically that this is a guarantee of this method. If the training converges, then we can prove that this model on the left is an actual valid explanation of this model on the right. We cannot prove at the moment whether that is the unique explanation for that model, but we can prove that it is one correct explanation. The uniqueness is a work in progress that we're also working on at the moment. So this is now very nice because we can just generate a lot of causal models for any kind of behavior, any kind of process. Then we can train neural networks on them. And now we have neural networks for which we have an actual ground truth explanation of how the behavior occurs. And using this, first of all, we can test existing explainability methods because all the methods that I've listed at the beginning, they are in some ways subsets of causal abstraction. For example, SHAP, the method SHAP gives you a feature importance, and it tells you how much each input feature influences the output result. And once you have the correct causal abstraction for this model, you can simply compute it from this graph. You can just do a simple mutual information computation, and you have the actual answer. So using this, you can check how correct different explainability method may be and how useful they are on your particular examples. And of course, based on this, another nice thing is that we can use it to evaluate future explainability methods, which we hope will be based on causal abstraction. So for example, using this, then you can try to develop ways to extract an SCM from a neural network, because now you have actual data to test your different methods and to evaluate them. So thank you very much for listening. This was a bit short and high level, but I am now open to questions.
So it's on page 9. So about how to map the SCM to a neural network.
This one?
And yes. And for example, one question is how to make sure a particular component is performing some synthetic stats on the left graph. I don't know if I'm.
So you're trying to say how do we make sure that this part stores this?
At this particular layer and this particular block, which is performing the calculation.
So so this is what the training procedure itself read. I don't know if I have time to explain the whole paper, but what happens is that basically in causal abstraction, one of the main tools is intervention, meaning that we change something in the neural network and we check that the output is affected in the correct way. And this is kind of what happens here, is that to make sure that this state corresponds to a variable that is here, we will restore the these activations of a neural network, but on another sample, and we check that the output of a neural network will be affected as if you had done the same operation in the high-level causal model. So it's a bit complex and hard to explain, but the paper is quite well, and
okay.
I would recommend it.
Another question is that, for example, on a neural network, we have many choices. For example, on a hidden statement, hidden layers between the two blocks, we can add many layers, we can create any architecture, but how to choose the one to use in practice?
So here, this is very trial and error so far. It's really, you try to see if your neural network is able to store a variable somewhere, and you try to train it using that procedure, and either it converges or it doesn't. And if it doesn't, then maybe you didn't leave it enough space, give it enough activations. So as a lot of machine learning, there's a lot of experimentation and just seeing what works. Basically, at the moment, this is a recent paper and there hasn't been a lot of follow-up, so it's kind of just try to see what works, basically, at the moment.
thank you for your presentation. A little bit of follow-up of the previous questions. And the theoretical results that you mentioned, does it depend on the number of interventions? How is it obtained, in fact?
So in fact, there is some kind of sampling that goes on in this procedure. So this theoretical result that if the loss is 0, then the model is a valid causal abstraction. It would be technically if you perform the training and really the loss reaches 0 and you have infinite samples. Of course, in practice, we have to work with some kind of approximation. You have to sample your input variables in your causal model. So if those are continuous variables, you're never going to be able to map the entire space. So of course, there is some kind of compromise that you have to do with this.
Okay, thank you.
Yes.
Comme tu veux, mais je sais pas, tu peux faire, ok. So, Gérard. Oh, maybe not Gérard first. You, yeah.
So yeah, related to this, do you conjecture that you do have unicity of the causal model that creates the current graph?
So the answer is that with this method, as described in this paper, no. Actually, this is something that we've seen at the moment. You can find different mappings and different causal models where it still works. So this is another side project that we're doing, is trying to improve that method so that it guarantees unicity, or at least has some stronger sense of uniqueness.
If I understand well, you're doing this for generating benchmarks.
Yes, basically.
And you are, one of the issue, I would say, is that you're restricting the kind of explanation that will be provided by any system by the language that you take in your causal models. So you showed us, for example, 2 very different examples of explanation. And how do you know the space of explanation first? Because this is what you will need to do in order to say that for this network that I will give as a benchmark, there is only one good explanation, unique. That's the goal. But if someone show you something which is, totally clear, and but not part of your causal model.
So this is why the idea is to have a causal model that really represents everything and includes everything in the neural network and is unique. Again, this is not something that at the moment this method guarantees. But if you mean the language as in the causal model itself, it's a generic enough method that you should be able to model any kind of process that happens in the neural network. If you think about it, the neural network itself, it is a causal model. You can just take that each variable is an activation, and each edge is simply the weight of a layer from an activation to the next activation. So that is a valid causal model, and it explains the neural network fully. It's just not interpretable because it's not simple. It's the entirety of... Yes. So you're asking about the evaluation metrics for the benchmark itself? Yes, so the goal is to ensure that only one explanation is correct. Yes? Yeah, that's fair enough, but we need to start with something. It's like a benchmark will never fully represent what happens in real life, but at the moment, the methods of interpretability are not able to explain anything at all. So if we can explain something with at least one explanation, that would be a good start, because at the moment, we're not able to do anything.
So we can discuss. So before the DNN era, so 15 years ago, people were, I've been using DBN, so dynamic Bayesian network, which looks like very much your left side. Okay, so you can infer, in fact, causal networks from data, even in time. Just so you can have a temporal extension of the dynamic Bayesian network. So I think it would be very interesting, in fact, to some from the same data input to compare the old approach of DBN with the DNN approach.
So
you see there are some parallelism between the two.
So Bayesian networks are in fact a kind of causal model. So this is completely the same framework. The thing with this kind of method of causal inference is that they try to infer the graph here on the left from the data, so from X, Y, Z, and the different states. And here we don't know what graph we're looking for, and we have access to a neural network, which is not the data, but it's the process that transforms the data. Yes. Yeah, I agree. There's definitely lots of parallels and things that we can reuse.
Thank you. Ali, you can ask later. Later, I said. Please, my friend.
Based on mathematic, let's say, equation. Do you plan to do that on text or more?
Yeah, so this is an example with math, but and of course this is a starting point. But the goal is to have that with LLMs and so on.
Thank you. Thank you. Thank
Yes.
you. Thank you, Maxime.
Okay.
Thank you very much to all the speakers, to Didier, thank you very much. Okay, so it's now the end of the MIAI days. We still have our General Assembly, so we'll see how many persons are staying for the General Assembly. Maybe we will have it in the bar downstairs, I don't know, we'll see. So I just wanted to say a few words, and I would like Snejana, Maria, and Emeline to come here. I know they don't like to come to be up front, but please come and join me, because I would like to thank them, because I mean all these organizations and the organizations of many events that we have during have in MIAI, not only all the events but all the actions and activities in MIAI. Well, they were made possible thanks to Snejana, thanks to Emeline, thanks to Maria. Thank you very much. And to be frank, I bought a few. These are some chocolates. Okay, so so for the next step, that will be MIAI cluster, there will be some announcements on our website, and then there will be a few events that will be set that will take place beginning of September, right after the summer break, in order to start building our new MIAI in a way. So stay tuned, and there will be all this information here. So maybe we can take a 5-minute break. Sophie, Tang, I don't know whether you want to add something. So we can take a 5-minute break, and then we have our General Assembly. That will be something rather informal in any case. The thing is, I need a break. A very short break.